Ever pondered about how future technologies could predict events across various timescales and levels of detail? Welcome, dear listeners, to a world where this is not only possible but is being actively pursued. Enter the realm of the integrated reflective rewriting framework for co-inductive retrocausal backpropagation in omni-recursive, multi-scale Markovian temporal prediction systems. A mouthful, I know, but it's as fascinating and groundbreaking as it sounds. Imagine a technology that can assess its own performance, learn from it, and rewrite its own rules and structures for better outcomes. That's the power of reflective rewriting. But it doesn't stop there. This framework also incorporates co-inductive retrocausal backpropagation. It's a fancy way of saying that the system can refine its predictions by sending information backward through time, managing potentially infinite or self-referential causal loops. Incredible, isn't it? This system operates within omni-recursive multi-scale Markovian temporal prediction systems, meaning it can handle predictions across various timescales and levels of detail. It's like having a super-powered crystal ball that can zoom in and out of timescales at will, leveraging recursive processes and Markovian properties for efficient modeling. Now, you might be thinking, surely there must be a limit to such potential. This is where the hyper-theoretical approach comes into play. It's a blend of advanced theoretical constructs and mathematical formalisms that ensure the system's robustness and adaptability across diverse scenarios. It's like a theoretical safety net, ensuring the system can stand up to any challenge thrown its way. Couple this with the use of fixed-point combinators to manage recursive computations and ensure stable, convergent solutions. Add in the self-adjusting meta-rule optimization that dynamically tunes high-level rules and strategies to adapt to changing data patterns, and you have a technology that is as flexible as it is powerful. But what about paradoxes or inconsistencies? Enter dynamic causal consistency enforcement, which ensures that the system's predictions and retrodictions maintain a coherent and logically sound causal structure. Now, you must be wondering, what does all this tech jargon mean? Well, worry not, we will break it down for you. First off, let's unpack some of these terms. Reflective rewriting at its core is the concept of self-modification. It's a system's ability to change its own rules and structures based on its performance and understanding of the data it processes. Imagine it as a futuristic AI that learns from its past actions, then tweaks its own programming to become more efficient or accurate. It's like an athlete who watches their performance, pinpoints their mistakes, and changes their training regime accordingly. Now let's move on to co-inductive retrocausal backpropagation. It sounds complex, but let's break it down. Co-inductive is a way of handling potentially infinite or self-referential processes. Retrocausal refers to the idea that the future can affect the past, and backpropagation is a method of refining predictions by propagating information backward through time. So, in essence, co-inductive retrocausal backpropagation is a way for the system to refine its predictions by sending information back through time using co-induction to handle potentially infinite or self-referential causal loops. It's like having a conversation with your future self, where you can ask for advice or insights to refine your current actions. These techniques allow the system to be dynamic and adaptable, constantly learning and evolving based on the data it processes. It's not just about making predictions, but about refining these predictions over time, becoming more accurate and reliable. Imagine a weather forecasting system that not only predicts the weather but learns from its past predictions, refines its algorithms, and gets better with each forecast. Or a stock market prediction system that adjusts its strategies based on market trends and its own past performance, constantly improving its accuracy. Interesting, isn't it? But there's more to come. Let's delve deeper. Now hold on to your seats as we journey into the realm of omni-recursive, multi-scale Markovian temporal prediction systems. Imagine a system that can make predictions on various timescales, from the minutiae of seconds to the grandeur of millennia. That's exactly what we're dealing with here. This system doesn't just predict the future on a linear scale, it delves deep into various levels of detail, from micro to macro, providing a comprehensive overview of potential outcomes. At the core of this technology is the concept of recursion. Recursion, in its simplest form, is a process that repeats itself in a self-similar way. It's like a Russian nesting doll, where each layer reveals a smaller version of the same pattern. In an omni-recursive system, this process is applied across multiple scales, allowing for a level of predictive depth that is truly mind-boggling. But how does this system manage such a complex task? The answer lies in the Markovian properties it leverages. Named after the Russian mathematician Andrei Markov, a Markovian process is one where the future state depends only on the current state, not on the sequence of events that led to it. This allows for efficient modeling, as the system doesn't need to account for the entire history of the data it's predicting. It just needs to consider the present. By combining the power of recursion with the efficiency of Markovian properties, this system offers a multi-dimensional view of the future. It's like being able to see the intricate details of a mosaic while also appreciating the full picture. And the beauty of it is, the system is continually refining its predictions, learning from its successes and failures, and adapting to the ever-changing landscape of data it encounters. So we're not just talking about a static one-off prediction. We're talking about a dynamic, self-evolving model of the future that grows more accurate with each iteration. And all of this happens within a framework that maintains logical coherence, preventing paradoxes or inconsistencies in its temporal reasoning. Still with us? Great, let's move on to the next fascinating concept. Next, we venture into the world of fixed-point combinators and self-adjusting meta-rule optimization. Diving straight in, let's talk about fixed-point combinators. These are a unique breed of computational elements that help manage recursive computations. Imagine you're in a hall of mirrors, each one reflecting an image of you into the next. This is a bit what recursive computations can be like. A process feeding back into itself, creating a potentially infinite loop of reflections. Enter the fixed-point combinator. Like a well-placed mirror in our hall, it ensures that we get a stable, convergent solution. It steps in to manage these self-referential or cyclical dependencies, providing a mechanism to handle the infinite. With a fixed-point combinator, our system can work with recursive computations without getting lost in a sea of reflections. Now let's shift gears and chat about self-adjusting meta-rule optimization. This is where the system takes the wheel to drive its own improvement. It dynamically tunes its high-level rules and strategies, adapting to the ever-changing patterns of data it encounters. Think of it as a chess player who doesn't just learn from every game, but also changes the way they approach the game itself. They might start favoring aggressive openings, or perhaps realize that a defensive strategy works best for them. In the same way, our system refines its predictive accuracy over time through automated refinement. It learns, adjusts, and improves, not just playing the game better, but also playing it smarter. So, in essence, fixed-point combinators and self-adjusting meta-rule optimization work hand in hand, turning a potentially chaotic and static system into a streamlined, self-improving powerhouse. The former keeps the system grounded, while the latter ensures it never stops reaching for the stars. Exciting, right? But wait, there's more! Finally, we arrive at the concept of dynamic causal consistency enforcement. This is the linchpin that keeps everything in check, ensuring the integrity of the entire system. It's the gatekeeper, the final arbiter, the one that makes sure that everything adds up and makes sense. Imagine, if you will, a grand orchestra, with each instrument playing its own part. Each one is important, each one has its role, and together they create a beautiful symphony. But what if one instrument is out of tune or playing off-beat? The entire symphony is thrown off. This is where the conductor comes in, keeping everyone in line, making sure the music flows as it should. Dynamic causal consistency enforcement does the same in our predictive technology. It ensures that the system's predictions and retrodictions, that's predictions about the past, by the way, maintain a coherent and logically sound causal structure. It's like the conductor of our technological symphony, keeping everything in harmony. So how does it do this? It ensures that the rules of cause and effect are followed, that the laws of logic are adhered to. It prevents paradoxes or inconsistencies in the system's temporal reasoning. If something doesn't add up, if something doesn't make sense, the system flags it, examines it, and corrects it. And this isn't a one-off process. It's constant, it's ongoing, it's dynamic. Just as a conductor doesn't just start the symphony and then walk off the stage, our system doesn't just set things in motion and then sit back and watch. It's always on guard, always checking, always enforcing consistency. And that's what makes this technology so powerful, so revolutionary. It's not just about making predictions, it's about ensuring those predictions make sense, that they're reliable, that they're accurate. It's about creating a system that doesn't just crunch numbers, but understands them, learns from them, and improves upon them. And that, friends, is the future of predictive technology. A future where technology doesn't just predict, but learns, adapts, and evolves.